Hello everyone. Today I am excited to present a VTD visualization superscalar processor architecture. To make this complex inner working easier to understand, we have modeled the CPU component in a zero gravity anti-gravity space. Traditional block diagrams often fail to capture the dynamic simultaneous nature of a modern processor by letting component float freely separated by the space connected through to glowing energy pathways which represent our data buses. We get much clearer picture of exactly how instruction flows, plate execute, and coverage in truly parallel system. Step 1. The front end. Our journey starts at the top of the architecture. You can see glowing the particle entering the system. These are our program instructions. The first enters instruction fetch unit IFU. The IFU job is to pull the next instruction from instruction cache. From the IFU instruction flow down the energy pathways into instruction decode unit IDU. Here the raw binary instructions are decoded into micro-operation. The processor figures out exactly what operator needs to done, whether it's math, calculation, a memory load, or branch. At this stage, everything is still happening in strict sequential program order. Step 2. Dynamic scheduling and issue. Next, the decode instruction move into the heart of the processor dynamic execution engine. The scheduler in our model, this is visualized as a rotating hub, symbolizing how it continuously assesses and distributes the workload. Because the superscalar, the scheduler does not just send one instruction at a time, it intelligently issues multiple instructions simultaneously into stations reservation status. Because the stations act as a waiting room, an instruction might be stuck waiting for data from previous calculation to finish. As soon as its data tendencies are met, the reservation status pass the instruction of the execution unit. This is where the processor breaks away from a strict program order and begins executing instruction out of the order, maximize efficiency. Step 3. Execution and data set. Now we reach the core out of parallelism. Below the reservation status, you are multiple execution unit glowing working at the same time. We have three ALU arithmetic logic units handling basic integer and math logic. We have few floating point dealing with complex decimal calculation, and we have LSU load or store unit reading from writing and to memory. Notice the glowing particle stream shooting down into all them simultaneously. This is definition of instruction level parallelism. Multiple instructions are physically being processed in exact same clock cycle across different units. Of the side, you will notice the registration file. It is connected to all execution unit via live beams. As the ALU and FPU calculate result, they constantly read and write data back to the register file, sharing information instantly between the parallelism pipelines. Step 4. The backend and conclusion. Because our execution unit are finishing tasks out of order. Example, a simple ALU addition might finish much faster than complex FPU division. We need a way to restore the original program order. Otherwise, our software would crash or execute incorrectly. That is the job of the ROB or recorder buffer. All the execution unit funnel their finished result here. The ROB catches the completed instruction, sort them into back exact order from original, wrote them safely, retires them. Finally, the results move to the write back unit WBU, which officially commits the data memory or architecture register and shoots the finished out of the system. To conclude, what are seeing in incredibly chaotic, out of order, high parallel execution of a modern superscalar process. elegantly sorted back into perfect sequential order by time it output. Thank you, sir. I would happy to answer the question about the data flow and architecture blocks. Thank you.